Okay, so today I wanted to discuss general homotopy completeness and co-completeness of model categories. But before we do that, I want to sort of give a new spin on notion of equivalent junction, which stems from a more general approach by deformable functors. So the general topic is homotopical completeness. And completeness of model categories. But first we'll discuss deformable functors. Okay, so if x and y are just some homotopical categories, and we have not necessarily homotopical function between x and y, then f is said to be left deformable if f is homotopical on a left deformational retract of x. Okay, so that's the basic idea, and one can clearly see that equivalent functors are an instance of left equivalent functors are an instance of left deformable functors, because they're homotopical in a subcategory of cofibrant objects, which is, as we know, a left deformational retract of a model category. So that's the basic idea. And right deformable functors have those homotopical on the right deformational retract X. Okay, so next let's discuss deformable adjunctions. Well, those are just like equivalent functors. So here, instead of model categories, we consider arbitrary homotopic categories, and we say that an adjunction is deformable if f is left deformable and f prime is right deformable. So what is the point of considering deformable functors? Well, the idea is very similar to equivalent functors. We just want to have good approximations of these functors, meaning that they should be unique, and if we're really lucky, the composition of approximations will be an approximation of composition. So let's discuss approximations. Let me give a definition. Let f be a functor where x and y are homotopical categories. Then we say that a pair Ka is a left approximation of f, if Ka is homotopically terminal homotopically terminal object in the category over f. So we consider category of homotopical functors over f, and we take a homotopically terminal object. Normally one defines a right approximation of f. So what are the properties of these approximations? Well, they're pretty similar to what we discussed for Cleveland functors. So first of all, such approximation exists, it is unique. A necessary condition for existence of left or right approximation is left or right, respectively, deformability of f. And this manifests in the following statement. For any zero such that there is a left deformation of x into x0, and Rs is one such deformation. It means that the pair FRFS which belongs to the over category of the functor f is a left approximation. Dually one constructs right approximation from a right deformation. Okay, so now to a more tricky part. We want to have something similar to what we have with Quillen functors. Namely, we want to compose deformable functors and obtain a deformable functor. However, this is not the case, and the composition of deformable functors is not necessarily deformable. Or even if it is, it's not necessarily true that for example, a left approximation of composition of deformable functors is a composition of approximations. However, we can give certain sufficient conditions which ensure that we can actually compose approximations and everything works smoothly. So let me give such conditions. Okay, so assume that we have a functor between homotopical categories X and Y, and a functor between homotopical categories Y and Z. We say that a pair of functors is locally left deformable or right deformable. If there exists a left deformational retract F0 and another left deformational retract Y0, such that the following properties are satisfied. So first one is that F1 is homotopical on X0. This means that F1 is left deformable. Second is that F2 is homotopical on Y0, meaning that F2 is left deformable. Third condition ensures that the composition of functors is also left deformable. So it should be homotopical on X0. Hence also left deformable. Okay, so this was a condition of local left deformability, and for a stronger condition of just left or right deformability, we have the following condition. So F1 of X0 should be inside of Y0. Observe that conditions 1, 2, and 4 obviously imply condition 3, which makes this notion of left or right deformable pair of functors strictly, well, not necessarily strictly, but stronger than the notion of local left deformability. And another way to state left deformability or right deformability is using these deformations explicitly. So the fifth point states that there is deformation R1S1 from X to X0 and R2S2 from Y to Y0, such that F1 is homotopical on X0, F2 is homotopical on Y0, and F2S2, F1 are 1 from the composition F2R2, F1 are 1 is weakly equivalent to just the deformation of, to homotopical to depth approximation of the composition. So so yeah, that's an alternative statement which uses explicit deformations. Okay, so this last statement ensures that left or right deformable pairs behave nicely under compositions. So let me give a precise statement. So assume that we have a composable pair of functors. Such that this pair is left or right deformable. This means that, yeah, and additionally, plus X, Y, and Z are saturated, meaning that the localization map to the homotopic category of these homotopical categories inverts only with equivalences. So if this is the case, and the pair, and the pair is locally left or right deformable, and just left or right deformable. And we don't need the straightness condition. Yeah. So assume that we just have a left deformable pair, then the composition of the left approximations is a left approximation of composition. And actually, there is relatively not a simple, but sometimes simplifying way to verify that a pair of functors is indeed deformable left to right. So assume that we have a pair of composable adjunctions. Um, then, yeah, and here we really need the condition that X, Y, and Z are saturated. Then, if the pairs F2, F1 is locally OF deformable and F1 prime, F2 prime is locally right deformable, then the pair F2, F1 is left deformable if and only if F1 prime, F2 prime is right deformed. Okay, so now we can discuss the notion of partial adjunctions, which arise from deformable adjunctions. So as you recall, partial adjunction was something, some isomorphism between home sets on subcategories of cofibrant objects. And so here we have a very similar story. In fact, we can call this deformational retracts in some sense also subcategories of cofibrant objects. And then we would have partial adjunctions, which are isomorphisms between classes of, well, home sets and homotopic categories of certain subcategories. So let me write this down in more detail. Okay, so let F and F prime be deformable adjunction. Such that F is homotopical on 0 and F prime is homotopical on Y0, so F0 is a left deformational retract, and Y0 is a right deformational retract. Then F prime induces partial a junction such that for any object x in x0 and any object y in y0, there is a partial junction isomorphism, which works like this. So we take homotopy category of y, take the maps from fx to y, and this is isomorphic to homotopy classes of maps like this. So the properties of this adjunction are as follows. So first of all, it is natural in x and y. Then it is compatible with the adjunction f of prime, meaning that we have a commutative square where on top we have sort of non-derived junction, and on the bottom we have derived junction, partial junction. Okay, so now we can observe that many results including functors or results in including functors remain valid for deformable adjunctions. In particular, these are the results about the existence of derived natural isomorphisms for any two left approximations and so on. So let me just briefly recall what are these results. So if f between x and y, f prime between x and y is a deformable adjunction, then there are being functions u and u prime which assign to any two left respectively right approximations A1, A1, A2, A2. Of F and respectively K1 prime, A1 prime, K2 prime, A2 prime, right approximations of F prime. They assign derived natural isomorphisms, which are just isomorphisms of the form like this and respectively like this. With the properties that given U prime are natural in both variables. And second, that well, they respect the morphisms in the over category of the functors F and F prime respectively. So if we have map between two left approximations, for example, then its homotopization coincides with UK1, K2. This is just the result of homotopic uniqueness of left or right approximations. Okay, so going back to deformable partial adjunctions, to deformable adjunctions. Well, we can also prove that certain other results about equivalent functors are valid for deformable adjunctions, but I think, well, basically maybe it should be an exercise. What are the results from the previous talk? Hold also. A hold for all deformable adjunctions. Okay, and so I think I'll end this well, sort of, I don't know, comment on deformable adjunctions with adopting equivalent condition, which we had for discovering when certain equivalent adjunction is in fact equivalent equivalence for deformable adjunctions. So okay, so assume that we have a functor. Sorry, we have a deformable adjunction. Then the pair F prime is set to satisfy equivalent condition if there is so if first of all there exists a left deformation of x into x0 such that f is homotopical on x0. I'll write deformation of y into y0. F prime is homotopical y0, such that for any x in x0, y in y0, a map like this is a weak equivalence in homotopical category Y. If and only if it's a joint map is a weak equivalence in homotopical category X. And this condition is equivalent to the requirement that well, this is equivalent to requiring that for any such x, y, and 0, the condition holds. So not only on certain left and right retracts x, x0, y0, but on any such left and right retracts. Okay, so now we can move on to discussing homotopic completeness and co-completeness, but first I want to briefly discuss the usual notion of completeness and co-completeness, and in particular colimit and limit functors. Okay, so assume that X is a category and, well, that X and D are both categories, not necessarily small. Then a D colimit or D limit functor X is the left or right in the case of limit joint of the functor C star from X to XD, which sends an object of X is sent to the constant diagram of shape D, where each object of D is sent to X, and each morphism is sent to the identity morphism on X. And similarly, yeah, so colimit then is a left adjoint, which goes from the category of diagrams to X. We can generalize this notion, assume that we have an arbitrary functor between two not necessarily small categories A and B, and we say that U colimit or U limit on X is a left or right adjoint of the functor which changes the indexing category of the diagram. So it can be denoted by XU or equivalently by U upper star, and it goes from XP to XA. So it just composes each diagram with U, and we obtain a diagram, each B diagram it composes with U, and we obtain an A diagram in X. And so the colimit functor then goes in the opposite direction and is a left adjoint. Analogously, if we have two composable functors between small categories, so we have category A, B, and D, then if there are functors of U colimit, V colimit, and VU colimit, there are natural transformations which will be denoted like this. And these are the transformations between the composition of two colimit functors to the colimit functor of the composition. And so the similar holds for limit functors. And so this natural transformation is a conjugate to the identity natural transformation which we have between the composition of functors between diagram categories. Sorry. Yeah. So these definitions imply that and so from the fact that this is adjoint to this identity transformation follows that this natural transformation is in fact an isomorphism. And now we observe that colimit and limit functors are composable. So assume once again that we have two composable functors between index categories. Then if all three colimit functors exist, It means that the colimit of actually we don't need distance of this, because if we have just these two colimit functors, then their composition is a VQ colimit. Okay, so now I want to discuss one more property, namely compatibility of colimits with adjoints. So colimits are compatible with left for colimits and right for limits and joints. What this precisely means is that assume that we have an adjunction between categories X and Y, and we have a functor u from A to B. And then assume that that TS is a pair of colimit or limit functors on X and Y. So T is a colimit functor on X, and Y S is a colimit functor on Y. Then the compositions FBS and TFA, which go from diagram category on category of A diagrams in X to category of B diagrams in Y. Are left joins of the composition. The following composition. So we take the induced diagram functor, we compose it with GB, and we obtain same thing. This composition. So and we obtain the functor in this direction. Sorry. Okay, and since they're left adjoint, it follows that they're naturally isomorphic. Okay. Now we can discuss notion of complete and co-complete categories without any homotopical context. So category X is called co-complete or complete if for every small category D, exists a D colimit or a D limit in case of completeness. And if this is the case, then one can deduce, I'll show how we can deduce it in just a moment, that so if one is true, then for any functor between small categories, there exists U colimit or U limit. The way to show this is to construct certain categories which index certain categories colimits over which are just the colimits are just a colimit for a functor U. So let T be an A-shaped diagram in X, and we want to send it to certain B-shaped diagram in X, or a functor from B to X. And this diagram is constructed by sending so this thing here sends B and B to the following colimit. So we take another category of the functor B of the functor U, we take this category, the functor U over the object B, and we take a colimit of this functor on the colimit on the functor J upper star T, where J is just the forgetful map from this category to A. And it might be tempting to think that we can organize all these colimits over. So we basically defined what is a colimit over a category and what is a colimit over a functor. And it might be tempting to think that for an arbitrary category, or at least a sufficiently co-complete one, we can organize all this data into some sort of colimit diagram indexed by the category of small categories. So we know how this colimit should be defined on objects and how it should be defined on morphisms of functors. However, there is certain problems which arise from the fact that each time we have to choose some specific adjoint. I mean, there can be many colimits, all of which are obviously naturally isomorphic, but still they are not unique. So instead of diagram, we obtain only something known as colimit system on X, which I will define right now. So Okay, so let G be a category. Then diagram category XD is okay. So sorry, I started on the wrong foot here. So what is a colimit system? Well, colimit system is a function which goes from category of small categories to just well, a collection of not necessarily small categories. And so this works like this. So on objects, so if D is a small category, then it is mapped to a not necessarily small category of diagrams of shape D in X. Second, if we have a functor between small categories, we map it to a certain U colimit Fu from X, well, formally speaking, from Fa to Fb, but we know what that means. It means from say to Xb. And if we have a composable pair of maps U and V, or pair of functors, if this is a composable pair, then f of uv, or vu rather, is a conjugate fvu from the composition fv fu to f of the composition. So this is a conjugate of the identity natural transformation. So it can be shown that such colimit system exists on X if and only if X is co-complete. This is not very hard to prove. I mean, we just established that all colimits should exist in this category, because you can always consider a functor which collapses an arbitrary small category D into one object, one morphism category. And category of diagrams over such category is precisely X. So we established the fact that all small colimits should exist in X. And one can construct such a colimit system on X by just, so let me say that colim cut is a colimit system that's defined by calling cut of u being certain fixed adjoint, which is denoted by column u. So the idea is that we just fix for each functor, we fix an adjoint and call it u column u like this. And for each composable pair of functors, the value on this pair it's a fixed natural transformation between these fixed adjoints. Okay, so now we discussed all the preliminaries, and now we can discuss the notion of homotopical completeness and cocompleteness, which are constructed in parallel to the usual notions of completeness and cocompleteness. So let me start by discussing homotopy colimit and limit functors. So now we once again return to the setting of a model K-square, and we will just well, we will use the notion of homotopical K-square from time to time when need arises. So let M be a model K-square. And assume that D is some small K-square. Then, first of all, homotopy equal limit or D limit the limit functor on M is a left or right approximation of the functor of the colimit functor of the usual colimit functor, which goes from K-square of D diagrams into the model K-square itself, or in the case of limit, it goes in the same direction, but it should be a right adjoint. Okay, so in the same vein, we can define for an arbitrary functor between small categories a notion of a homotopy u colimit or u limit, which is constructed as a left, respectively right approximation of the functor which goes from between so of the usual u colimit functor which goes from A diagrams to D diagrams in M. And since what we're constructing are left and right approximations, such homotopical limits or limits are homotopically unique if they exist. And actually, you can say more for model categories, they did always exist. So for every model category M and a functor between small categories U, first there exists homotype U colimit or U limit functors in M. Second, every homotopy U colimit or U limit functor Ka on M has a derived adjunction which looks like this. It is important to note here that the functor of the induced diagram descends to homotopy categories because weak equivalences are defined in functor categories object-wise. So the induced diagram functor is a homotopical functor, unlike the colimit functor, which is not necessarily homotopical. And so these derived adjunctions are associated with a pair of approximations for the adjoint pair. So with a pair of approximations for the adjunction on categories of diagrams. So this pair of approximations is just this homotopical U colimit itself and the functor of induced diagram with an identity natural transformation. So the co-unit of this adjunction is the following homotopical functor. Sorry, the following direct initial transformation. Here, E is a natural transformation which comes from the junction of colimit and the induced diagram functor. Okay, so this is the proposition that we'll prove in a few minutes. Now, homotopical colimits, homotopical limits and homotopy limits are, as well as regular colimits and limits, composable, meaning that if we have two homotopy colimits which are constructed from two composable functors, then we can compose them, and what we'll obtain will be weakly equivalent to the colimit of the composition. Okay, so once again, M is a model category. U and V are two composable functors between small categories. And assume that Ku, Su, or Au, and Kv, Av are homotopy colimits for these functors. Okay, then, first of all, their composition, which is defined as a composition of functors, and a natural transformation, which is defined like this. So this thing here is a transformation which goes from the composition of colimits to the colimit of the composition, and AV, AU are defined using the following square diagram. So we have AVKU, which goes to this composition of functors. Here we have KVAU, which goes from KVKU to KVU colimit. And finally, here we have colim V, AU, AV, colim U, and we obtain colim V, colim U. And so this composition this thing here. Is a homotopy VU colimit. And the second part is that the composition of derived junctions is a derived junction for the composition. Okay. Finally, the final parallel with what we had for usual colimits is that homotopic limits are compatible with the junctions. However, here, since we have model categories, we don't consider arbitrary junctions, we consider equivalent junctions. So homotopical compatibility with equivalent junctions. Okay, so let's assume that we have equivalent junction between two model categories. And we also have a functor between small categories. So this is equivalent junction. And we say that F is homotopically compatible with the homotopy U colimit, and G is homotopically compatible with the homotopy U limit. And let me provide a rigorous explanation of what all this means. So the idea is that the compositions of colimit functor and the functor induced on categories of diagrams by the functor F is weakly equivalent to the composition of in the other order. So we take first they take a functor on diagrams, and then we take a colimit. And well, this is basically the notion of compatibility for left adjoints. So let me write this down. We have a category of diagrams like this. we go to a category of diagrams like this. We take the function induced on categories of diagrams, and we can do this in other direction. Namely, we can first go from categories of diagrams, from category of diagrams in M to category of diagrams in N. And then we can use the co-limit functor to obtain the same final category of diagrams in in M of shape B. So these compositions are naturally weakly equivalent, canonically weakly equivalent, and the same holds for homotopy U limits and functor G. And moreover, not only, sorry, I think that, yeah, that's not right. Okay, what is right is that this thing here is not only weakly equivalent, it is in fact isomorphic, because we're considering just usual co-limit and co-limit functors and usual categories. We just at this stage we don't care about model structure. But then we can consider the composition of say that Ka is a homotopical limit, namely it is a left approximation of this functor column U, and assume that, so this is a column U on M. And then we have K tilde A tilde, which is the left approximation of column functor on N. Then the compositions FB K tilde FB A is naturally weakly equivalent, canonically weakly equivalent to the composition K tilde FA A tilde FA. So this happens in homotopy category of in a homotopy category of approximations to the functor, to the co-limit functor. So this canonical weak equivalence happens in well, this will be a pretty clunky notation, but I think I can write like this. So we take all homotopical functors from MA to MB, consider it over column U, and what we obtain is we consider it over FB column U, and turns out that this composition of approximations is in fact an approximation of the composition. So this is the statement about compatibility with colonial junctions. Okay, but we haven't proved anything yet. So now I want to formulate the key result, which will allow us to prove the statements above about existence, composability, and compatibility with colonial junctions. So this result will require some further work to prove because it relies on Reedy theory, theory of greedy model structures on functor categories. But nevertheless, we can formulate it now and use it to prove these statements about homotopical limits. So let me formulate this. So assume that M is a model category, D is a small category. Then we can define a full subcategory inside the category of D diagrams in M, which consists of a category of virtually cofibrant objects. And what is the use of this full subcategory? Well, first of all, and obviously we can do this dually, namely define a subcategory of weakly fibrant objects, but I will write only the sort of left part of this story, and you can later fill in the gaps if you want to. So the subcategory of virtually cofibrant objects is a left deformational retract of the category of all diagrams. This is the first useful property. And the second one is that if we have equivalent adjunction, and we have some small category D, then we can consider the functor from the category of diagrams to another category of diagrams. And as it turns out, F sends weak equivalences inside of the subcategory of virtually cofibrant objects to weak equivalences inside of subcategory of virtually cofibrant objects in M. That's another useful property. In particular, it implies that the Cleveland functor is homotopical on this subcategory of virtually cofibrant objects. And finally, what we have is that if M is a model category and U from A to B is just some functor, then the colimit functor from diagrams of shape A to diagrams of shape B sends weak equivalences on virtually cofibrant objects in M in virtually cofibrant objects in this category of diagrams to weak equivalences on category of diagrams consisting of cofibrant objects. So now I think I want to finish my talk by proving the results of the statements formulated above, except for this last one. Okay, so let's start with existence. Okay, so this is actually not that hard because in the previous statement, we have shown that the Coulomb U function is in fact is left deformable. Why is that? Well, we've just established that right here, I think, that the colimit functor is homotopical on the subcategory of virtually equifinite objects, which is a left deformational retread of the category of all diagrams. So this means that the functor Coulomb U indeed has a left approximation. Okay, so the second thing we want to prove is that there is in fact a well-defined composition of homotopical limits, which yields a homotopical limit of composition. So to do this, we observe that M is saturated. So composition. So M is saturated. Hence, all diagram categories are also saturated. Because weak equivalences are defined object-wise. And the pair M, V, MU is left deformable. Sorry, it's right deformable. So this pair is right deformable. And also the pair Coulomb U, Coulomb V is locally left deformable. Assume that RS is a left deformation from MA to the subcategory of virtually equifinite objects. Then we have a commutative diagram which looks like this. And so this diagram, after taking homotopizations, gives rise to the following diagram. So we take homotopization of KR, homotopization of U upper star. We take homotopization of K, homotopization of U upper star, homotopization of this functor, which exists because column U is homotopical on the subcategory of virtually covariant objects. We take homotopization of U upper star, and this all finishes like this. So we have natural transformations into the identity functor on the homotopic category of diagrams of shape B and M. So this is the proof of the first part of the statement about the composition of colimit functors. And the second part about the composition of the colimit functors, which states that the composition of derived adjunctions is the derived adjunction of their composition, follows from the fact that the natural transformation from natural transformation from homotopization of K composed with the homotopization of U star to one of to the identity transformation of the homotopic category of diagrams is obtained by just considering this thing here, which is just which is precisely this natural transformation. Finally, we want to prove that Coulomb functors are finally, we want to prove that I'm sorry. So sorry. No, I'm terribly sorry. This thing here only proves this only proves existence of derived adjunction for homotopical limits. This does not prove that we have the desired result about the composition of so about the composition of colimit functors. So this is the second part of existence, and about the second part of the composition, which I mistakenly stated that this was proven. which asserts that the composition of derived that the composition of derived adjunctions is a direct adjunction of the composition, requires the following quite large diagram, which gives us the desired result. So let me try to write it down. So it works like this. Okay, so maybe it's not quite comprehensive, but the idea is that we repeatedly use the natural transformations, which are co-units of the colimit induced diagram adjunction, and we obtain the diagram like this. So E something, so is a co-unit of the adjunction, colimit something, something upper star. And we repeatedly use this adjunction to obtain this large commutative diagram to see that the top row induces an adjunction associated to the composition. So we go from the composition of two deformations and two induced diagram functors. And the bottom row induces the co-unit of the adjunction which comes from the composition. So we so this is the co-unit of the adjunction which comes from the homotopical element of the composition. the composition junction. This shows that indeed the composition of direct junctions is the direct junction of the composition. Okay, so this proves the statement of, oh, this proves the statement about the composition. And I think I want to end here for today. Thank you for attending. Let me stop the recording.